So, we will talk about Zeeman effect. If you remember that we have talked about Stark effect, which is splitting of the spectral lines in presence of a weak electric field. Now, we will talk about Zeeman effect, which is we talk in a general sense, I mean not related to hydrogen atom now, but then we will talk about it later. So, as the plan goes that we will talk about Zeeman effect in an external magnetic field, and of course, it is a weak magnetic field that we are going to talk about. And then we will talk about normal Zeeman effect and anomalous Zeeman effect. And then we will talk about this intrinsic magnetic field, and in that connection we will actually talk about hydrogen atom and splitting of levels of the hydrogen atom. In that connection we will talk about spin orbit coupling as well, and we will see that we need to find a suitable basis for expressing our operators, and so this all these traditional wisdom of writing the wave functions of the hydrogen atom for calculating the the correction in energy due to these this electric or I mean due to this magnetic field will now no longer remain same. So, the psi NLM will no longer be used as a basis for writing this this problem or this Hamiltonian, and we need to find a new basis, and this would bring us to the total angular momentum J, which is still a good quantum number in presence of a spin orbit coupling. Okay. So, Zeeman effect was of course seen by Zeeman in 1896. So, it was initially being looked at by Faraday, and then it was observed by Zeeman in 1896. So, there are two kinds of Zeeman effect that we talk about. One is called as the normal Zeeman effect and the other is anomalous Zeeman effect. And so, the normal Zeeman effect actually occurs when the transition between the spin singlet states arise. So, what we mean by spin singlet state is that the MS value, that is the azimuthal or the magnetic quantum number rather, corresponding to the spin, just like angular momentum we have L and we have these quantum numbers as L and M. Now, we have to write L and ML, and this is precisely for the reason that we are also going to talk about spin, because spin is the one or rather the degree of freedom that is going to couple with the external magnetic field. So, now we will have to talk about S and MS, and so this is the magnetic quantum number associated with the S operator, and we rename this M, which we used earlier so far, which was associated with the angular momentum, the orbital angular momentum. Now, we call it as ML. So, the Zeeman effect would arise when MS is equal to 0, and this is called as a normal Zeeman effect. So, the other one is anomalous Zeeman effect, which occurs when the total spin of the initial state or the final state or both is non-zero, which means that MS is not equal to 0 and MS is finite here, and that is called as the anomalous Zeeman effect. In general, there is no difference between the two, there is no fundamental difference between the two, but we will discuss each one of them. So, let us see what is normal Zeeman effect, and so that corresponds to S is equal to 0, and so the spin is equal to 0. That would tell you that J, which is equal to L plus S, which is the total angular momentum, which is the sum of the angular the L, the orbital angular momentum and the spin angular momentum. This is simply equal to L. Okay. So, the energy splitting that one gets is equal to delta E, it's minus mu dot B. So, this is in presence of a magnetic field. So, this is minus mu dot B, and suppose if you have B in the Z direction. So, B in Z direction, then the dot product will only involve mu Z and B, and so this mu Z is nothing but equal to minus ML, EH cross over 2m, where make a distinction between ml is the magnetic quantum number associated with the orbital angular momentum, and this m, when it's written alone, means the mass. Okay. If it helps by writing m as mass of the electron, please do that, EL or something, or simply write it as m, but make sure that you know that it in the denominator it involves the mass of the electron. Okay. So, this is equal to nothing but minus ml mu b, that is the Bohr magneton. So, your delta E in terms of these quantities, we have ml EH cross by 2m into b, and this is nothing but ml into mu b b. So, this is the delta E that we have, that is a splitting between the energy levels which are because of a weak magnetic field. This one has to make a mention that B is weak, and when I say weak, what it is weak compared to, it's weak compared to any spin orbit coupling that may be there, which is going to be the second part of the discussion that we make. So, the change in energy or rather the splitting in energy in a magnetic field due to these in this normal Zeeman effect, where there is no S, it is only L, or the orbital angular momentum. Then it involves the orbital angular momentum magnetic quantum number, and then the Bohr magneton and B. And so, there are 2L plus 1 energy levels. So, 2L plus 1 energy levels, because ml actually varies from minus L to plus L through 0. So, this is 0 and to plus L for any value of L. So, there are these 2L plus 1 levels for a given value of ml. So, one can actually show the transition between these L equal to 2 and L equal to 1 levels. Okay. So, we are just talking about this azimuthal quantum number, which is rather this orbital quantum number, which is L, and between these L values we are considering the transition, and you see that this will cause a transition like this. So, this is ml. So, this is L equal to 2, which will have 5 levels because it is 2L plus 1, and this ml will have these values plus 2, plus 1, 0, minus 1, minus 2, and each one would have sort of splitting that is given by EH cross by 2m E. Here it is written explicitly the mass of the electron. So, we can make it as E here and E here. So, that would be this ml mu b b, which is this EH cross by 2m into b. So, that is the splitting that you see, and it is a uniform splitting for L equal to 1 and L equal to 2. And now, these are these 9 transitions that you see, which corresponds to delta ml is equal to plus minus 1, or the mod of delta ml equal to 1. So, what is meant is that you see from 2 it goes to 1 ml equal to 2 to ml equal to 1, that is this one, and then from 1 to 0, and then 0 to minus 1, and then there are 1 to so there is this one is from 1 to 1 here, and these are the ones for which delta ml is equal to 0. So, these are those ones, because there is ml equal to plus 1 to plus 1, 0 to 0, and minus. So, this is from minus 1 to minus 1, and so on, and then we have the other 3. So, there are 9 lines that you see would arise in Zeeman effect. So, if you do an experiment involving the L equal to 2 and L equal to 1 states. So, suppose you talk about n equal to 3, that is a principal quantum number equal to 3, then you have the L values that are allowed are 0, 1 and 2, and you are now looking at the transitions that could take place between these L equal to 1 and L equal to 2, which will have all these 9 transitions that are possible. So, 3 with so delta ML is equal to 1, and these would correspond to delta ML equal to -1 and so on. So, this 0 to 1 here. So, let us call it as a -1, and these ones will correspond to delta ML equal to 0. So, these 9 transitions will be seen, and what you have is also that these the energy or the frequencies associated can be found out. So, there are 3 distinct transition energies. And these 3 distinct transition energies are E0 plus, which is E0 is just your unperturbed energy, which is EB H cross by 2 M E E0, and this is E0 minus EB H cross by 2 M E, and so this would correspond to delta ML equal to +1. This corresponds to delta ML equal to 0, and this corresponds to delta ML equal to -1. Okay. So, what is the frequency associated with this transition? And the frequencies are nothing but this is omega equal to plus minus EB over 2 M E or 0. So, these are the frequencies that are associated, and these frequencies can be recorded in the spectroscopy measurements. So, these are the transitions that one sees in normal Zeeman effect when you have S equal to 0, which means MS is equal to 0, which means J is purely equal to L, and we are characterizing the states by L and ML. Okay. So, the anomalous Zeeman effect, this occurs, as I said, that when the total spin is finite. So, total spin corresponding to the initial state or the final state or both, they are finite. And so, here of course, your S is not equal to 0. So, J is equal to L plus S will have to be now taken, and both are finite. So, the total magnetic moment that comes here is the following. Mu is equal to minus G L mu B L by H cross minus G S mu B S over H cross, and here of course, we have G L equal to 1 and G S equal to 2. This is pretty close to 2, and then the total magnetic moment takes the form minus mu B over H cross, and it is L plus 2S. Okay. This is also true for if you put S equal to 0, you can get the this normal Zeeman effect. And what we can see is that we can draw a vector diagram like this. This shows these L, this is that vector inside, which is by the blue color, which is here, and then you have a S vector which is here, and the vector sum of these two vectors is the vector J. So, you can put a vector sign if you like, and then this is the magnetic moment associated with the orbital angular momentum. This is the magnetic moment associated with the spin angular momentum, and this is that mu, which is the vector sum of mu L and mu S, which is written here. Okay. So, in this case, this delta E, that is the splitting between the energy levels for this spin, where the spin is finite of these initial and final states. I mean, either the initial state or the final state or that of both. Now, we have to use the quantum number corresponding to J. So, this is equal to G m J E h cross B divided by 2 m E. And this is nothing but equal to G m J and mu B B. So, mu B is the Bohr magneton, which is E h cross by 2 m, and so G is called as a Landé-G factor, and which has a form which is equal to G equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2 J into J plus 1. That is the Landé-G factor. So, one can take an example of for this doublet sodium doublet line splitting between these. So, this example could be sodium doublet lines involving 2 p half. So, that is L equal to 1 and 2 p half thing, and then it is 2 p 3 by 2 and 2 s half. And if you draw these lines, they look like these transitions that you see there. So, you have a 2 p 3 by 2, which has of course 5, and then 2 p half has 2, and there is 2 s half that is there. So, there are 10 transitions which are shown by these vertical lines, blue lines, and so there are 10 transitions in total. And in this particular case, we have these the energy splitting is given by this. So, this is for large magnetic field, but anyway that is not required because we are not talking about large magnetic field. So, let us just keep it here itself that there are 10 transition lines, and this is specifically for weak fields. And something more interesting happens when you have the spin orbit coupling to be important, which is the case that we are going to discuss. And in presence of a spin orbit coupling, that acts like a magnetic field itself and will give rise to splitting even without an external magnetic field to be present. And this spin orbit coupling is an important sort of parameter, or is an important factor in deciding many of the material properties. So, we will do that, and we will do that in connection with the hydrogen atom. So, it is an intrinsic Zeeman effect that we are going to talk about. Okay. So, the basic structure of the hydrogen atom, which is the simplest one that we know, that we have a proton here and an electron here, and the electron goes round in this circular orbit around the proton, around the nucleus. And you can make a simple assumption for the moment, and it can be shown, which I am not going to show explicitly, but can be shown that that approximation does not alter things in a big way. Let us just talk about the electrons moving in a rectilinear path. So, there is a straight line motion of the electron instead of a circular motion, and in fact, because to take into account the circular motion, you just have a trivial factor which is sort of used here in this connection. So, we will think that the electron is moving in a straight line, which because of which it is like a wire of charge, and where charge is flowing, of course, where current is flowing rather. I mean, so because of that, there is a magnetic field that will be produced at the location of the nucleus or at the location of the proton. Okay. So, the proton will actually feel that magnetic field because of the electronic motion, because the electrons moving means there current flowing in the circuit or in the, say, along a wire. Now, if you think that in the rest frame of electron, the proton is actually moving in an orbit, okay, and think that the proton is actually like moving in a rectilinear path, then at the position of the electron where the electron is situated, there will be a magnetic field present there. So, we are now looking at the rest frame of the electron. There is a magnetic field due to a charge which is nothing but coming from proton is moving in its vicinity. If that is acceptable to you, we have a way to calculate that magnetic field by a formula called as a Biot-Savart law in classical electromagnetism, and which tells you that this elemental magnetic field due to a small section of the current that flows into the wire is given by mu 0 over 4 pi I into dl cross r divided by r cube, where r is the distance between the current flowing and where you want to calculate the magnetic field. Here the current is flowing because of the proton, and you want to calculate the electric field at the electron. So, this r is the distance between or difference in position between the electron and the proton. And you see what is dl? Dl is nothing but, so I dl is the current element that flows in the wire because of this motion of the proton, which is a charged particle, positively charged particle. So, this is that that current that flows in the small length element, and because we are talking about a small length element and what is the corresponding magnetic field, we have written elemental notation, that is dB here and dl here. Okay. So, if you want to get the full magnetic field, that is not difficult. So, this is equal to minus mu 0 by 4 pi, and we have this charge, this is equal to V cross R, and this is divided by R cube. And what you do is that you can multiply and divide by a 4 pi epsilon 0 and a 4 pi epsilon 0. Okay. And so, why we have used a negative sign is that your I dl by definition is equal to minus q v, because the current flowing and the direction of the when you multiply it by the charge, where q is the electronic charge. So, E is equal to the corresponding electric field you can find out from this relation that you have, you can also find it out from Coulomb's law. So, this q r divided by 4 pi epsilon 0 r cube. Okay. So, that is the electric field and that is the magnetic field, and what kind of relation do they have in between? So, B is equal to minus mu 0 epsilon 0 and a V cross E. And if you remember classical electromagnetism, mu 0 epsilon 0 1 by root over of that is equal to C. So, this is nothing but 1 over C square. So, this is 1 over C square V cross E. So, that is the magnetic field that is generated at the location of the electron due to the motion of the proton. Okay. And the electric and the magnetic field, the corresponding magnetic fields are related by this equation, where c is the speed of light. All right. So, we can put this expression for B or rather E, the electric field, equal to minus 1 by c square, and so this is P over m, which is nothing but V. We are using the non-relativistic formula here. So, this is equal to Z over R cube and the R vector, and where we have used a q over 4 pi epsilon 0 is equal to E. Okay. And so, this gives you minus Z E divided by m c square R cube and a p cross R. Those are the vectors that you see here on the first line, and p cross R is reminding you that the angular momentum is the moment of the linear momentum, which is written as R cross p. Since it is a p cross R, we will get a minus sign. So, put together we will have the writing this magnetic field in terms of the angular momentum of the electron is an important thing. In fact, these m is the really the electronic mass that we are talking about, and this is L. So, this is an important relation for us, that the magnetic field that is produced at the location of the electron, where the electron is located, situated. Now, we are talking about the rest frame of the electron. So, the electron is actually at rest in its rest frame or in its own frame. Okay. So, that magnetic field that is generated can be written in terms of m c square R cube L, and this result is important because the spin of the electron, which is S, is going to couple with this B and giving rise to a L dot S coupling. So, let us we'll use that as a perturbation term and do a perturbation theory that we have learned so far. So, we have a perturbation term, let us call that as you can call it anything, but let us call it as H prime with a Z. Z means it is pertaining to the Zeeman term. So, this is minus mu S, that is the magnetic moment corresponding to the spin quantum number. So, it is mu S dot B, and this we have discussed just a while back, that this is minus G S E over 2 m and S vector, and G is almost equal to 2, and this is called as this Landé factor, and we can use this H Z prime to be equal to E G S over 2 m and Z E over m c square R cube and S dot L. Okay. So, this is mu S, sorry about that. So, this is actually mu S. So, it is S dot L, and this is our perturbation term, and we have to do a perturbation theory using the hydrogen atom, the states of the hydrogen atom. But that poses a problem, and we are going to talk about the problem in details, but this S dot L term makes some of the quantum numbers that we are familiar with in this notation of N L. Now, allow me to put a ml here, because now there are going to be different kind of magnetic quantum numbers associated with L, associated with S, and maybe even associated with J. So, this is no longer going to be a good basis to calculate the correction due to this intrinsic Zeeman term. Okay, and we will have to learn how to negotiate that difficulty. All right. So, if you absorb all the terms in some kind of this constant, so what we have is H Z prime, which is important for us, is nothing but some f of r, and we have L dot S or S dot L, does not matter. I mean, you can write it because these are dot product, and some other coefficient which involves all this mass, the GS, the Landé factor and all that, charge, nuclear charge and all that, I mean the atomic number, speed of light. So, C has all of that included, Z, E, M, E, mass of electrons, which you have not written, I mean we have written it only in terms of M, and GS. Okay. So, we absorb this, and then of course, we know that f of r is actually 1 over r cube. Okay. So, this is important because when you calculate the correction, you have to consider the radial part of the hydrogenic wave function as well as the orbital, I mean the angular part as well. Okay. So, the angular part will have these kind of terms will be useful, and for the radial part it is only this, and the radial part is not going to have any effect on the L dot S term or S dot L term, and similarly the angular part will have nothing to do with this f of r. Okay. So, we are debating whether psi n L m m l now is going to be a good eigenfunction for this Zeeman term, and now for that, because now you have spin, you have to take a product with this S m s, and where S is equal to half, because we are talking about just electrons. So, S is equal to half. So, m s, which is the magnetic quantum number associated with the spin, this operator is equal to plus half and minus half. Okay. So, we will have a term which is, and whose states are, so this chi S m s can be written as a 2 component spinner having these values. So, we can write this the wave function, the total wave function, let us write it with a psi, and this is going to be like psi n L m m l, and then we have you multiplied by a 1 0 spinner or a 0 1 spinner, depending on whether you have m s equal to half or m s equal to minus half. So, this is m s equal to half. Well, when I say half, I actually put that h cross is equal to 1. Okay. So, remember that, because h cross sets the scale of the angular momentum. So, this is m s equal to minus half. So, we have written a wave function, but we are not sure whether the wave function is a valid wave function for this particular problem, but then at least we are able to include spin into this eigenfunction of the hydrogen atom, and which now no longer becomes simply a function of r theta and phi, but it also acquires a 2 by 2 structure because of this spinner. So, we can now write this thing down in terms of n, L, m l and m s, and instead of writing it as these bases, we can use this ket. This is the principal quantum number, orbital quantum number, magnetic quantum number corresponding to L, and magnetic quantum number corresponding to S. So, the question is that, is it a good basis for us? Okay. And if it is a good basis, then we do not have to worry about anything, and we can simply use this basis in order to calculate this the correction due to this term. But unfortunately, it turns out that it is not a good basis, and we will give you the reasons for that. Okay. So, first let me explore point number 1. So, let us call it 1, and explore that S dot L f of r, okay, f of r is 1 over r cube, whether that commutes with L square operator, because while framing the solution for these hydrogen atom, we have fallen back on the L square operator and the Lz operator, and used their eigenfunctions to denote the theta phi part of the solution of the hydrogenic wave function. And so, let us look at this thing and convince ourselves if this is a good operator, because it has to commute. If it commutes, then they have same set of eigenfunctions. And so, we have this as h z prime L square. So, this is nothing but h z prime, this is what we have written. Okay. So, h z prime L square minus L square h z prime, and this is nothing but equal to L square, and we don't really need to worry about that f, because L is purely a function of theta phi. So, wherever you want to write f, it does not matter. So, f is only a function of r. I am not even writing the radial dependence. So, it is simply f, say for now, and it is L square and s dot L minus f s dot L into L square. Okay. So, that is what we have to. So, it is basically the L square is actually a vector operator. So, this is L square. All right. So, what is the first term? That is this term. So, let us write down the first term, and the first term is nothing but this is equal to L square s dot L. This is equal to f, and we write it in terms of components. So, this is like I L I square, or rather this is not L I square, this is L square, which is L x square plus L y square plus L z square, and because it is a dot product, we can write it as S I L I sum over I, okay, where I is x, y and z. All right. So, this is L square S I L I, and because S I commutes with L square, they operate on different spaces, because one is in the spin space, one is in the orbital space. So, we can write this down as f and sum over I S I L square L I. Okay. And we can also commute these two. So, we have done these two here and write this, and L square of course commutes with any of the Lx, Ly or Lz. So, I can one can write this as f and Si Li L square, and so that is nothing but the second term, which is here. So, this second term and the first term they are same, which means that this commutator is equal to 0, which means that this H z prime commutes with L square. That tells something interesting, that tells you that L continues to be a good quantum number. All right. So, they would share the same eigenfunction. All right. So, that at least some property that helps us, because we need to know what is the eigenfunction for, or what is the appropriate basis for solving this problem. Okay. So, 2 is that H z prime does not connect, and I am going to prove that, connect states which have different L values. So, it sort of keeps the different L values separate and they do not couple, which means that if you are trying to take a trying to calculate the matrix elements of these H z prime operator between two L values, say L equal to 2 and L equal to 1, then it is 0, and how we can show that is the following. So, let us write L square, and we can write it n L m and all that, but what is important for us is just psi L, and this is L into L plus 1 H cross square psi L. So, be consistent and put H cross everywhere. We have not put it at some places, but if you want, you can write it as H cross by 2 and minus H cross by 2 and so on and so forth. Okay. So, here we have put it, and then now we want to calculate. So, this has a definite L. It has also M and ML and so on and so forth, but also has a N of course, but we are just interested in this L value. So, now we take this psi L and calculate this commutator h z prime and these L square and these commutator which is different L which is say L prime. So, this is equal to psi L h z prime L square psi L prime and a minus psi L, and you have a L square h z prime psi L prime. Okay, so, this is between these two states. So, now this L square will operate on this L prime and will give me a L prime into L prime plus 1, continue writing that h cross square and will give me a psi L and a h z prime and a psi L prime. So, L prime into L prime plus 1, and this will give me so minus L into L plus 1, because this L square is going to act on these bra psi L. So, this is h cross square and you have a psi L h z prime and there is a psi L prime and so on. So, this can be simplified and one can write it as L into L plus 1, L prime plus 1. You can take this h cross square common as well. This minus L into L plus 1 h cross square, and then you have a psi L h z prime psi L prime, it's equal to 0. Now, why it's equal to 0 is that because this commute. So, we could have written down the 0 right from the beginning, but this is equal to 0. This commutator between the psi L and psi L prime is equal to 0. Now, that tells us that either this is equal to 0 or this is equal to 0. Okay. So, this is equal to 0 when L is equal to L prime and then this is not equal to 0, and when L is not equal to L prime then this is not equal to 0, that is the first square bracket is not equal to 0, but the these expectation value of psi z prime is equal to 0. So, it is either L equal to L prime, which makes this equation to be satisfied, or you have this psi L h z prime psi L prime is equal to 0. So, that tells you that h z prime does not connect the L quantum numbers, different L quantum numbers, and that is an important thing, and probably it's helps. Okay. The third thing that we need to check is that this h z prime L z is not equal to 0, and that is easy to see because your these h z prime involves Lx Sx plus Ly Sy plus Lz Sz, and it does not commute with Lz because the Lz with either Lx or Ly is not equal to 0. Okay. So, which means that ML is not a good quantum number for this Hz prime problem, that is a Zeeman effect that we are talking about. So, it is not a good quantum number, and hence you cannot use these ML or rather psi NL ML, which we have been using so far even in the case of Stark effect and so on. So, in this Ket notation NL, ML, MS is not a good basis. And when I say good, I mean that whether we can calculate the matrix elements in this basis or not. And clearly, because this is not a good basis, we should not be using it in trying to calculate the energy correction due to this Hz prime term. All right. So, 4 is that, but there is definitely a solution to this problem, and the solution is that you use this total angular momentum, which is nothing but L plus S. This is what we have seen as well. okay, and we can actually use some basis which is involving J and Mj in order to get this correct basis or the proper basis to calculate the matrix elements. And how do we sort of go ahead? We can write this J dot J, which is equal to a J square, which is equal to L plus S whole square, and here we get a L square plus a S square plus a 2 L dot S. Okay. I think you can convince yourself that L dot S and S dot L are they would commute, and it means that they can be added together to get a 2 L dot S. In general, you should not use the A plus B whole square formula to get this to expand the expression, because A into B may not be equal to B into A when A and B are arbitrary operators. In this particular case, L acts on the coordinate space and spin acts on the spin space, so L and S would commute. All right. So, J has this, or rather the J square has eigenvalue which is J into J plus 1 H cross square. Okay. L square, which is known to be a good quantity, has eigenvalue L into L plus 1 H cross square. So, while you actually go through this in some books, they might have dropped out this H cross or put H cross equal to 1. So, be sort of be aware that sometimes one does not want to carry on with this H cross and is put equal to 1. S square in a similar fashion can also be a good quantum number whose it's S into S plus 1 by H cross square. So, if you put it there, so your L dot S can be written as it's a J square minus L square minus S square divided by 2. Okay. So, this L dot S has eigenvalue which is equal to half. Now, this J into J plus 1 J into J plus 1, or I put the H cross square outside, minus L into L plus 1 minus S into S plus 1, and that is the eigenvalue for this. But then we have not talked about what exactly is the state that we are referring to. And now this J, be very careful, J can take values, this is important thing. So, J quantum number will take values between L minus S to L plus S. Okay. So, Mj will take values minus J to plus J through 0. So, there are 2 J plus 1 values. All right. So, now we are closing in identifying what the state is going to be, which are going to be eigenstates of J and L square and S square and so on. So, that brings us to this fifth point, that we have these J square and Jz, whether they are they are good operators for us, and if we explore the L dot S term, remember the f of r is 1 over r cube, it is not entering into the discussion at all. And so, this is equal to nothing but Lx Sx plus Ly Sy plus Lz Sz, and this commutator with Jz, which is nothing but Sz plus Lz, that we have to see whether it commutes in order for it to be a good eigenfunction. And if I open up this, so it is Lx Sx plus Ly Sy plus Lz Sz and Lz plus Lx Sx. plus Ly Sy plus Lz Sz Sz. This needs to be seen, and the commutation between this two terms is not important here, because they would commute anyway. That is what I meant. I mean, this terms you can leave it, because Lz Sz with Lz is definitely equal to 0, and Lz Sz again with Sz is also definitely will be equal to 0. So, what we need to check is that whether Lx Sx plus Ly Sy, the first two terms, that commutes with Z, and the same goes for Sz, that Lx Sx plus Ly Sy, that commutes with Sz. Okay. And so, we have now 4 commutators, which are Lx Sx Lz plus Ly Sy Lz plus Lx Sx Sz plus Ly Sy Sz. And this is simple, because Lx Lz will give you a minus IH cross Ly. So, let me carry on in the next page, which is you have this L dot S, you are calculating L dot S and seeing it with Jz, and this becomes equal to Sx into minus IH cross Ly. Remember, Li Lj commutator or Si Sj commutator, this is both equal to IH cross epsilon Ijk. Either you have Lk or you have Sk. Okay. So, this is the first term, and then you have a term which is Sy into minus IH cross Lx, and this minus sign is because you have broken the cyclic. So, it is Lx Lz, Lz Lx would have been IH cross Ly, but now since it is other way around, then it is minus IH cross Ly, and Sx of course commutes with that. Similarly, Ly Lz is IH cross Lx, so it is Sy S Ly Lz. Ly Lz is IH cross, there is no minus sign there. So, this is Sy, and then we have these the other two terms, which are Sx Sz, which is again minus IH cross Sy Lx minus IH cross Sy Lx, and that is coming from this bracket, or we can put a, don't need to put a square bracket anymore, we just have this. And what is the last term? That is Ly Sy Sz. So, this is equal to IH cross Sx Ly plus IH cross Sx Ly, and you see that they cancel this, the first term cancels with the last one, and the second one cancels with the third one, and then we have it equal to 0, which means that Jz commutes with H2 prime. So, they will have Hz prime has common eigenfunctions with Jz. Okay. And we have also of course seen that, or you can check this, that L dot S with J square it commutes, because J square has terms which are L square, which I have already shown. In the same spirit, you can show that it commutes with S square, and of course, it has another term which is L dot S, which would commute with L dot S. Okay. So, that tells us that now we can have a basis which is either N, J, L and M J, Okay. So, these all are valid quantum numbers. Okay. And you can also have one corresponding to N, J, L and S, and because S is also a good quantum number. Now, if you have an ambiguity in basis that the term or rather the Hamiltonian or the operator that you are trying to diagonalize can be can be diagonalized in one basis, and it's also possible to diagonalize it in another basis, then these two bases will be connected by some unitary operation, and these are called as the Clebsch-Gordon coefficients. Okay. Anyway, that we will come later, but let us not just go ahead with N, J, L and M J basis, and we have now N, L or rather N J. The N is the principal quantum number which will always be there, N J L M J, and we have a H Z prime and N J L M J. This is equal to which is what we have found out, that it is j into j plus 1 minus L into L plus 1 minus S into S plus 1, and then it is NL, this has to be taken with f of r, and NL, remember these are these log-ware polynomials which are given as RNLR. Okay. And this S is nothing but, for our case it is half. So, this term becomes 3 by 4, it is half into half plus 1. So, what we have is the following, that we have to multiply this of course with 1 over r square, and suppose that problem is given to you, or you do not have to solve that problem. So, it is 1 by r to the power n between the eigenstates of the hydrogen atom, these are known, and suppose in this case we do not. So, let us just write it f of r, f of r goes as 1 over r cube, and RNL of, so this RNL of r, RNL of r, it's suppose given, it's a z cube divided by a0 cube n cube L into L plus 1 L plus half. So, that is the result for this, and now we have everything that we need. So, we have these H Z prime, which is the first order correction, Zeeman correction, because taken between the eigenstates of the hydrogenic atom. We had to work a lot to find the correct eigenstates, and that is where most of this energy went. But however, we have been able to find at the end, and this is equal to h cross square by 2, and we have a j equal j into j plus 1 minus L into L plus 1 minus a 3/4 and multiplied by these term. Okay. So, this term which is nothing but this term, okay, which is f of r, expectation value of that, and this is nothing but equal to h cross square over 2, and because j can take some values which are, in this particular case j can take values which are L plus half and L minus half, because S is equal to half, we have told this before, L minus half, and now we have this whole thing can be written as either it is L or it is minus L minus 1. This will be there when j equal to L plus half, that is the first one, and this will be there when j equal to L minus half, and the whole thing will be written as. So, let me write down, and then of course, this term that you have, I mean the same term with f of r. So, h z prime, which is the Zeeman term, the splitting or the energy correction due to this intrinsic spin orbit coupling or intrinsic Zeeman effect. And why it's called spin orbit coupling is that because L is sort of tagged along with S, or L is coupled to S. That's why it's called spin and orbit are coupled, and for that we needed to find a basis, which is what we have done. And it's L and L plus 1 with the sign, and now we have these E0 and Z square alpha square. So, we write it in terms of these energy scales of the hydrogen atom, which is 2 NL, L plus 1 and L plus half, and that's it. I mean, that will be along, I mean, this gives you this E0 is given by minus E square by 2A0 and Z square by N square. Z is of course equal to 1 for hydrogen atom, and this is the called as a fine structure constant, which is equal to E square by H cross C. So, this is nothing but the N J and we have taken L and Mj. So, Nj, Ml and Mj Hz prime, and this Nl, Nj, Ml, Mj. Sorry, what did I write? It's L. It should be L, not Ml. That's a mistake. Ml is not a good quantum number. So, Nj, Lmj, Nj, Lmj. This is the first order correction in the Zeeman, in the sort of intrinsic Zeeman effect. Okay. And this is what we wanted to find. We have done that for the Stark effect in presence of electric field. Now, we have done it for magnetic field, both as an external magnetic field and for the intrinsic magnetic field, which is because these are charged particles and the electron is actually revolving around the proton, constitutes a current in the rest frame of the electron. The proton is going around it and it constitutes a current again. And we have made an approximation that they are moving in rectilinear path, and have claimed that this approximation really does not have too much of bearing on the results that we had derived or obtained for the energy correction for the Zeeman effect. So, that concludes this Zeeman effect, and we have already done Stark effect, which are real problems, and they have been done in experiments. People have experimentally found that these are really observable effects for the hydrogen atom. So, we will stop here, and we will carry on with more perturbation theory problems or approximate method problems in the next class. Thank you.